Hey everybody, I am re-recording this lecture because as a part of the in-class activities that we did during this content day, we did a lot of project-related stuff and it was just very hectic in the room. So I'm re-recording so that we have just the lecture content all in one place. So this lecture is all about rigid body work and energy, because up until this point we have done work energy and conservation of energy only for particles. Okay, so today we're extending from particles to rigid bodies. All right, so I'm going to write just a little bit of notes. So the principle of work and energy for a rigid body is no different than the same relationship for particles. And what I mean by that is that we still get this exact same equation. We say the kinetic energy at time 1 plus the sum of all work done from 1 to 2 is equal to the kinetic energy at time 2. Okay? So this is still kinetic energy at time 1. This is still kinetic energy at time 2. And this is still work done by forces. The only difference is we get this, well, not the only difference, but one of the big differences, and torques. Work done by forces and torques from 1 to 2. So that's one of the differences. The other difference is what all contributes to kinetic energy. So a rigid body can actually have two different sources of kinetic energy. One source of kinetic energy is caused by that body's translation, and the other source is caused by that body's rotation. Okay, so if we're talking about all the things that should be considered when we try to fill out T1 and T2, when we have a particle just translates. So we just have that the kinetic energy of a particle is 1/2 mv squared, where v is the speed of the particle. But for a rigid body, we say that there's kinetic energy because of translation, which is equal to 1/2 mvg squared. And there's kinetic energy due to rotation, which is equal to 1/2 ig omega squared. Now, it's really important for us to notice on the rigid body equation, we have these subscript g's, right? So a particle is made up of only one point. A particle is made up of only one point. So if we want to talk about the speed of a particle, we're obviously talking about a speed of that individual point. But a rigid body, maybe if I draw my rigid body potato here, a rigid body is made up of an infinitesimal number of teeny tiny points. And we know from our rigid body kinematics section that every single one of these points can potentially be moving at a different velocity. So when we go to try to calculate the kinetic energy due to this body's translational velocity, we need to understand which particle's velocity is it that we care about. And it turns out that the one we care about is the center of mass point, or that point G. Okay, so we're talking specifically about the translational speed of this point G, the center of mass of this body. Then when we go to look at the rotational kinetic energy, we have the mass moment of inertia of this body rotating about an axis that goes through point G specifically, and then we have the angular velocity of that rigid body. Okay, so because a rigid body can both rotate and translate, both of those types of movement contribute to the overall kinetic energy of the body. Okay, now work done. Let's remind ourselves of how we calculate the work done for a particle. Well, here we just take the force that we think is doing work and we dot it with the displacement of the particle. And that actually stays the same. So if we have a force acting on a rigid body, we still get the force dotted with the displacement of the particle. Actually, I need to double check that. I believe this is the displacement of the point where the force is applied. Let me just triple check that real quick for us. Energy. I believe this is correct. I believe that you want to look at the displacement of the particle where the force is applied. Okay, and then we have this new moment. We have this new contributor to work, which is the work done by a moment or a torque. And that is equal to the moment dotted with the change in angle of the object. Okay. All right. So these are the changes we have. We simply use the same work energy equation, but now we have both a translational and a rotational component to kinetic energy, and we have a translational and rotational component of the work done. Okay, so let's make this more concrete with an example. All right, so the 30 kilogram disc shown below is pin supported at its center. Determine the angle through which it must rotate to attain an angular velocity of 2 radians per second starting from rest. It is acted upon by a constant couple moment, m equals 5 Newton meters. The spring is originally unstretched and its cord wraps around the rim of the disc. Okay, so we could write our known. We could say omega 1 is 0 because we start from rest. Omega 2 is 2 radians per second, because that's what it's asking about. We know that m, the external couple, is 5 Newton meters, and the spring starts unstretched. Another piece of information we'll need to know for this problem is that arc length is S equals theta R. Okay, so what is it asking us about? It's asking about a change in velocities. So it's asking about a change from 0 to 2 radians per second over some angular displacement. Okay, so whenever we hear a change in velocity over some displacement, that should be our light bulb that work energy is probably going to be useful to us. Okay, and then what is it asking us to find? It's asking us to find that delta theta. How much does the angle need to change in order for us to reach that angular velocity of 2 radians per second? Okay, so let's think about maybe really quickly which direction is this thing going to rotate. So initially, the spring is unstretched, so there's initially no force coming from this spring. Weight is acting down, but this thing is pinned, so we know that it can't translate anywhere. The only thing acting on it that would cause it to start spinning is this moment. Okay, so it's going to begin by turning in the direction of the moment. So it's going to start spinning in this direction. But this moment is constant. It never changes. It's constantly 5 Newton meters. But as we start rotating, this spring is going to become stretched and stretched and stretched and stretched as it wraps around the rim of the disc. So while the spring starts out with a force of 0, that force is slowly going to get bigger and bigger and bigger and bigger going in this direction, which is going to counteract this 5 Newton meter moment. So what I suspect is going to happen is we're going to begin rotating in the direction of the couple M, and we will start to get up to speed. We'll get up to 2 radians per second, but then we're going to slow back down as this spring gets further and further stretched. We're going to slow down until the spring force is equal to our external couple M. And then if we go any further, the spring is going to start to win. Okay, the spring is going to become the greater couple. Okay, so the net couple will become the direction of the spring force, not the direction of M anymore. So we're going to begin rotating in this direction, but then as we rotate further and further and further, we'll slow back down, and eventually we will start spinning back in the other direction. So what we're going to find actually is that there are 2 solutions to this problem. One is going to give us how far does it need to rotate this direction to get up to 2 radians per second. And then the second solution is going to say after the spring starts winning, it's actually going to get back up to 2 radians per second, but going in the opposite direction. Okay, so it will hit this value of 2 radians per second twice. Once as it spins to the right and once as it spins to the left. Okay, so now let's start looking at these individual terms of our work energy principle. So let's talk about the kinetic energy at time 1. Well, we know that a rigid body can have 2 sources of kinetic energy. We have kinetic energy due to translation, which is 1/2 mvg squared. But this disc on the pin can never translate, right? That point that represents the center of mass, point G, it's never going anywhere because it's pinned, okay? So this is going to go to 0. So there's no translational kinetic energy, but there will be, we need to assess whether there will be rotational kinetic energy. So rotational kinetic energy will be 1/2 Ig omega 1 squared. But actually this is going to be 0 too because we start from rest. Omega 1 is 0. Okay, so T1 is equal to 0. Just because it's easy, let's go ahead and fill out T2. So again, this thing can never translate. So its translational kinetic energy at T2 is 0. But it will have rotational kinetic energy. because it will be rotating at 2 radians per second. Okay, so IG for a disk is 1/2 mr squared, which is 1/2, what is the mass of this thing? 30 kilograms. And the radius is 0.2 meters. Okay, and omega 2 is 2 radians per second. So this should be 1/2 times 1/2 times 30 times 0.2 squared times 2 squared. Okay, so that's T2. And then we need to assess the work being done. So let's look at work done from 1 to 2. And for work, I always like to draw my free body diagram. We have supports from the pin, an OY and an OX, external couple M, MG, call this X and this Y. Oh, and then we also have the spring force. Okay, so now the question is, which of these entities on the free body diagram are doing work? Well, OX and OY are not doing work because they're pointed right at the pin, which never moves. MG is not doing any work because the point G never moves. The couple is doing work, right? Because the work done by a couple is U due to M is M times the change in theta. And then the spring is also going to be doing work. Okay, so the work done by a spring is 1/2 KS squared, where S is the change in the stretch of this spring. So we have a couple of things we need to figure out. What is the spring stiffness of K? Looks to me like that is 10 newtons per meter. So this is equal to 1/2 times 10. And then what is the change in stretch? Well, it starts out as 0 stretch. So we have -0. And then what is the final stretch? Well, the final stretch of the spring is going to be equal to however much of the spring wraps around the disc, right? So that's going to be whatever arc length of the disc that we spin through. So the arc length we know is going to be theta times the radius of the disc, which is 0.2 meters. So this is stretch final minus stretch initial. And this all needs to be squared. Alrighty, I'm going to call this delta theta to keep consistent. And then this M here for the work done by the couple is, of course, just the 5 Newton meters. Okay. However, we need to be a little bit careful about our positives and negatives. So we said we're going to start out assuming that we spin to the right, which is a good assumption, right? Because the couple is the only thing that could be causing us to start spinning. So we're obviously going to start spinning to the right. So we'll assume that our motion is to the right. Assume motion starts out clockwise. So the couple moment is doing positive work, but the spring is doing negative work because it's opposing that spinning. Okay, so we actually need to put a negative here. Okay, so now we have our 3 components of the work energy principle, so we should be able to just plug those back in. So let me grab our overarching equation again. Let's paste. And I'm going to fill in. So we said T1 is equal to 0. So this is 0. The work done from 1 to 2 is the work done by the couple, which was positive 5 delta theta, minus the work done by the spring, which is 1/2 k change in stretch squared, which was delta theta times 0.2 squared. And that's all the work. And then T2 was just this rotational component. So equals to 1/2 hold on 1 second. I'm just double checking something. Okay. 1/2 times 1/2 times 30 times 0.2 squared times 2 squared. Okay. So what do we see? We see that we have one equation with one unknown, and the one unknown is delta theta, which is what the problem is asking us to find. Okay. So you should be able to do the algebra here and solve that delta theta actually, sorry, let me give you a few more details here. What you'll end up finding is you'll have a quadratic equation. And so what we want to do is solve, so we'll change this equation into more of the canonical quadratic form. So if you rearrange enough, you should get minus 0.2 delta theta squared plus 5 delta theta minus 1.2 equals 0. And then we can use the quadratic equation to solve. Right, so if this is A, this is B, this is C, then we have x equals negative b plus or minus square root b squared minus 4ac all over 2a. And the plus gives us the first solution, and the negative gives us the second solution. Okay, so the first solution we get should be 0.2423 radians. And that's our final answer. Okay. Let's do another one. Make this a little bigger. Okay, the pendulum consists of a 10 kilogram uniform disc and a 3 kilogram uniform slender rod. If it is released from rest in the position shown, determine its angular velocity when it rotates clockwise 90 degrees. It looks like I need to give you one little trick that can be done. This is a special case. If we have a rigid body doing fixed axis rotation, we can use a simplified form of our kinetic energy. So, kinetic energy for a rigid body doing fixed axis rotation can be written, kinetic energy is equal to 1/2 I-O omega squared, where point O is the fixed axis of rotation. Okay, and if we do this, then this is the full kinetic energy of that rigid body. So the alternative would be to first find out where is where is the center of gravity of this thing, which might be probably over here, right? Because it's not going to be the center of the slender rod, because we have this big heavy disc at the end. So G is probably over here. And this point G, when this thing rotates, this point G is going to be translating, right? It's going to be moving down and to the left. So we would have some translational kinetic energy of G, but then we would also need to know still the angular velocity of this entire rigid body, because the entire rigid body is also rotating. Okay, so if we did not use this simplified form, we would have to say that kinetic energy for the full rigid body is equal to 1/2 mvg squared plus 1/2 ig omega squared. Okay, we'd have to do both of those terms where we're using point G for the velocity and point G for the mass moment of inertia. Okay, so notice here we're using the mass moment of inertia about point O, or in our case, in this problem, it's point A, the fixed axis of rotation. Okay, so it's a little bit of a simplification. All right, so we do, in fact, have a rigid body doing fixed axis rotation. So let's use this simplified form. But in order to use this simplified form, I need to know what is the mass moment of inertia for this body rotating about the z-axis that goes through A. Or we could call it O. Okay, so I-O is going to equal I-O for the disk plus I-O for the thin rod. And if we go back to our reference sheets for our standard shapes, we should be able to find that the mass moment of inertia of a thin rod rotating about its endpoint is 1/3 ml squared. But for the disk, we'll need to do the parallel axis theorem. So we'll need to say that I-O for the disk is Ig for the disk, which is 1/2 mr squared, plus the mass times the distance from G to O, which would be 2 meters plus 0.4 radius. So 2.4 squared, mr squared. Okay, so overall we should get that I-O is equal to 1/2 times 10 times the radius of the disk, which is 0.4 squared, plus 10 times the parallel axis distance, plus 1/3 times the mass of the disk, the mass of the rod, 1/3 mass of the rod times the length of the rod, which is 2 meters squared. So we should get 62.4 kilogram meter squared. Okay. Why are we doing all this? Well, because it's asking us about a change in velocity, a change in angular velocity, that's occurring over a change in angular displacement, right? So release from rest, and then it has some non-zero velocity after it rotates a displacement of 90 degrees, okay? That tells us we need to use work energy. Okay, so work energy is, of course, T1 plus some U1 to 2 equals T2. Let's do T1. The kinetic energy of this rigid body at time 1. Well, at time 1, it's released from rest, so there's no translational velocity and no angular velocity, so this is 0 because it starts from rest. Let's do T2. T2, we know that it is going to be rotating about this fixed axis of rotation. And so the kinetic energy at time 2, we can use this simplified form, which is equal to 1/2 I-O omega squared. And omega here is what it's asking us to find. It says find the angular velocity at time 2. So this is going to be 1/2. I'll go ahead and plug in I-O. That's 62.4 times omega squared. Okay, and since we chose that simplified form, that is the entire kinetic energy at time 2. And so last thing we need to figure out is the work done from 1 to 2. And so let's draw a free body diagram. So I'm going to draw this whole kind of lollipop looking thing where we have pin forces here and here. We've got the center of mass of the slender bar. This will be 1 G point, and so that'll be mg. So mass is 3 kilograms times 9.81. And then we have G for the disc, and we have another mg working there, so 10 kilograms times 9.81 working there. And then we can't forget this external couple of 30 Newton meters. So that's here, and that's 30 Newton meters. Okay. All right. So it looks to me like there are 3 things that are doing work. OX and OY are not doing any work because point O never translates either up or down or left or right because it's fixed. The couple does work because this thing rotates a total of 90 degrees. So let's do U1 to 2 is equal to U from the couple. It looks like the mass of the slender bar is doing work because this slender bar, this point G, is going to move downward as this thing rotates. So U from the rod weight. And then similarly for the disc, we'll have work done for the disc weight. Okay, to figure out exactly how to fill in each of these, I sometimes also like to draw the second orientation. That can sometimes help. So I'm actually going to move this down a little bit. And I'm going to draw in a different color the new position when it's rotated 90 degrees. G here and G there. And the reason this helps is because it makes it easier to see how much has each of these G's moved in the vertical direction. Okay, so G for the slender rod is going to be halfway down the slender rod, which will be 1 meter from O. So this is 1 meter. And G for the disc is going to be this distance from O, which is 2 meters plus the 0.4 radius. So 2.4 2.4 meters. All right. Okay, so let's fill this in. So the work done by the couple will be the torque times delta theta in radians, so pi over 2. The work done by the rod weight will be mg times the displacement in the direction of mg. So I go from a height of 0 down to 1 meter. So this is 1 meter in displacement in the direction of that force. So of course that's going to be positive. And then the disk weight is also going to do work. It goes also from a height of 0 all the way down to this 2.4 meters. So this will be mg times its displacement, 2.4. All right, so now we have all three of our work energy components, so we need to fill in our details here. So copy, paste. All right, we determined that T1 was 0 because everything starts from rest, so this is 0. U from 1 to 2 is just above here. So U from 1 to 2 will be 30 times pi over 2 plus 3 times 9.81 plus 10 times 9.81 times 2.4 equals T2. And T2 is this expression here. So 1/2 times 62.4 times omega squared. And that leaves us with one equation with one unknown, and the one unknown is what the problem is asking us for, which is the final angular velocity. Okay, so we should be able to solve that omega is equal to 3.16 radians per second. All right. So that's all for rigid body work energy content. I hope this helped, and I will see you guys in class very soon. Thank you. Bye-bye.